of the IVT. And let's draw a picture of first. So let's draw a picture of the setup of the IVT. So the IVT says you have this continuous function defined on a closed interval. And you have some value m that's between f of a and f of b. All the IVT says is there must be some place where the graph has to cross that line. And let's even pick out that particular location that I pinned down. So let's see, this input that I even drew was supposed to be like, I picked it to be like the last place where that happens. So let's try to think of that to figure out how the proof is going to go, because I want to decide what solution to the equation I want to turn, because apparently there can be more than one. So let's see, this place that is like the last place where y is equal to m. Just thinking intuitively, should there be any inputs to the left of that x value where f of x is less than m? I don't think so, because if there were, then by the IVT, the thing that we're trying to prove, so admittedly, this better not actually be in our logic, otherwise we're indulging in circular reasoning. We would have to come back up through the line y equals m, and then we would see a later place where that happens. So we wouldn't have actually picked the last one at all. So for every x value after this c, f of x apparently is bigger than m. On the other hand, it sure looks like there's stuff to the left where f of x is less than or equal to c. So here's a way to try to solve this equation. Let's think about the inequality. F of x is less than or equal to m. That'll give us like a set, the set of all numbers where f of x is less than or equal to m. This c is then like the supremum of that set. So there's like the language we have to describe our solution. So let's start going through the proof. The proof of the IVT. Let's let f from a to b to r to be continuous. Rho log, let's assume that f of a is less than or equal to f is less than or equal to f of b. And if they were flipped, maybe we'll try to convince ourselves we could come up with a parallel proof in that case. On the other hand, if you have a continuous function where f of a isn't less than f of b, then maybe you could just like, well, I could replace f by negative f of x. And then I would have these things being in the right order. So you could come up with a solution in the other case if you knew the solution in this case. So rho log, let's take this to be the case. Let's assume that f of a is less than or equal to m is less than or equal to f of b. And right, we get to assume that, right? Because, well, we want one of those two things to be true. So without loss of generality, let's assume the first. So as I said, I'm going to want to think about all x values where f of x is less than or equal to m. So let's just declare that to be a set. Let's set u to be the pre-image of negative infinity to m. And I don't know, let's just, as an aside, like write out what that means in terms of definitions. So in this set builder notation, that means u is the set of all x values where f of x is in negative infinity to m. Right, because that's what the definition of preimage is. Well, what does it mean for f of x to be in the interval from negative infinity to m?
It's less than or equal to m.
Yeah, it's less than or equal to m, where it is f of x. So this is the same as the set of all x values where f of x is less than or equal to m. So let's study that set. Let's study all x values where f of x is less than or equal to m. And somehow like the supremum of that set should be what the answer we're looking for. But let's start with this. When does the set have a supremum? What types of sets have suprema?
Bounded, non-empty.
Bounded, non-empty sets. So step one, let's show that that set is bounded and non-empty, not necessarily in that order. And maybe we'll even start with this. Let's start by justifying why it's non-empty. So by looking at this picture, can you tell me an x value that you already know has f of x less than or equal to m?
F of A.
Yeah, f of a. So that means a is in the set U. Because by assumption, f of a is less than or equal to m. F of a is in negative infinity to m. And so by the definition of our set U, a is in U. Yeah, that's good enough. Thus, U is not empty. That's good. Now let's try to come up with an upper bound. And maybe we'll use this same picture. What is an upper bound on this set? Let's. How about just B? I mean, maybe we'll even draw the picture in this case. So, in that case, that orange set appears to be the set U. And in particular, this orange set is a subset of A comma B. Because you're only allowed to take x values in the domain. But the whole domain is contained in A comma B. So, since this function has domain A comma B, this preimage must be contained in A comma B. Thus, B is an upper bound for U. Okay, great. So this set U is non-empty because it contains A, and bounded above because B is an upper bound. So it has a supremum. Let's let C be the supremum of U. I'm going to try to show that f of C is equal to m, and that sure looks like it happens at least in this cartoon picture. But cartoon picture does not make a proof. Let's try to do it. So let's see, what do we need? So we know that this C exists because the set has an upper bound. So let's look at all of the things that we need this C to satisfy. So we need a number C which is in the closed interval from in between A and B, for which f of C is equal to m. And right, in order to even talk about what f of C is, C had better be in the interval from A to B. So I don't know, this should be the easy part. Why is C in the interval from A to B? Let's talk through it. What upper bound do we already know this set has?
B.
B. And C is supposed to be the least upper bound, so what inequality can you deduce from that?
C is less than or equal to B.
C is less than or equal to B. We also know that A is in U, and C is supposed to be an upper bound on the set. So what inequality can you deduce from that?
C is greater than or equal to A.
C is greater than or equal to A. That's everything you need for C to be in the interval from A to B. Yeah, so let's just write that down. Possibly in that order. So we've already seen B is an upper bound on U. C is the least upper bound on U. So we can conclude that C is less than or equal to B. We've already seen that A is in U. Since C is supposed to be an upper bound on U, we conclude that A is less than or equal to B. I'll write it that way because, oh, don't, that's not what I conclude. A is less than or equal to C. I'll write it that way because now it's in the right order for me to write A is less than or equal to C is less than or equal to B. And so C is in the interval we need it to be. Everything feel pretty good so far? Okay, so the next thing I need to show is that f of C is equal to n. And if you like the step that we just did, like that might even be the step that you would just forget to do. Because maybe it seems so very obvious that why would you even bother checking it? But it seems important that the thing that you're going to plug into f of that will be in the domain of that. So let's prove that f of C is equal to n. I'll do it in two steps. I'll prove that f of C is less than or equal to n, and I'll prove that f of C is bigger than or equal to n. And let's resort to this picture to do it, to see how the proof should go. So let's see, this function is supposed to be continuous, right? So that means if I take another input that's pretty close to C, I'll get an output which is a good estimate for f of C. So let's see, it sure looks like if I look a little bit to the left of C, I get inputs which satisfy f of C less than or equal to 1. Inputs which satisfy f of x less than or equal to 1. But those f of x's are going to be close to f of C. So that means that there are things really close to f of C which are less than or equal to 1. Now take the really close to and make it really, really small. That should show that f of C is less than or equal to 1. Great, there's the first half of the proof. Let's now just talk through the details. So since I'm going to do all that estimation, I'll start by giving myself the freedom to make the estimations. If I can prove that f of C is less than m plus epsilon for every epsilon bigger than 0, I'll get f of C less than or equal to 1. All right, this was like the homework problem in the first homework, which I said this might seem like a really weird fact to say is important, but it is really important because now I have an easier inequality to prove. I've given myself that little bit of wiggle room. For every epsilon bigger than 0. So this is what I need to prove. I need to prove that f of C is less than m plus epsilon for every epsilon bigger than 0. So let's consider any epsilon bigger than 0. And I said this stuff about how, there should be inputs that are close to C that well approximate what f of C is. That's continuity, right? So let's just formally state that by expanding out the definition of continuity. So I've already declared this epsilon bigger than 0. F is continuous at C, so there exists some delta bigger than 0 such that, and you've already written what goes in the next line because you correctly told me what the definition of continuity is. There exists some delta bigger than 0 such that for every x in the domain a comma b, if absolute value of x minus c is less than delta, then absolute value of f of x minus f of c is less than epsilon. And there's the downside with me pre-typesetting the notes without knowing my handwriting size. I should start a little bit to the left. All right, so in this picture, the inputs we saw which gave us f of x less than m, or inputs that were just a little bit to the left of C. So let's look just a little bit to the left of C and see what happens. So if I'm going to start with the supremum and look just a little bit to the left, then I'm going to use like this reformulation of the supremum that had a delta in it. So what does that reformulation say? That reformulation says that there should exist some x in the set U such that well, let's see. Let's maybe remember it this way. So here's this C, which is the supremum of U. There's C minus delta. Could this possibly be an upper bound on the set U? Since it's not an upper bound on the set U, what can I conclude?
There's an x between them.
there's an x between them. So I can conclude that there exists some x in U such that c minus delta is less than x. And because you said between them, I'll put the less than or equal to c. All right, that's not part of the reformulation of the definition, but this is in U, and that's an upper bound on U, so you do get that. Why does that mean the absolute value of x minus c is less than delta? I don't know. Let's talk through it this way. So let's see. X is less than c, so is x. So how could you rewrite absolute value of x minus c without any absolute value bars?
C minus x.
Good. Oops. There. But now let's check this out. C minus delta is less than x. So x is bigger than c minus delta. X is bigger than c minus delta, so that should be less than c minus delta. But hey, that's exactly delta. People feel pretty okay about that? Okay, and I'm kind of just like following the steps given without caring about why, but let's put some things together. Absolute value of x minus c is less than delta. So what can I conclude because of this implication?
F of x minus the absolute value of x minus f of c is less than epsilon.
Cool. So, I mean, all that writing was just encoding this intuitive statement that x value is close to c will approximate f of c. But now let's remember this x is in U, which is the preimage of f inverse of negative infinity to m. So what can you tell me about f of x as a consequence? Well, how about this? X is in the preimage of this set. X is in f inverse of negative infinity to m. So it must be that f of x is in negative infinity to m. And yeah, I guess I've given myself space to write that, so let's write that. But what does that mean?
F of x is less than or equal to m.
Yeah, that's just definitions, right? So let's see, what do I have right now? I have f of x is less than or equal to m, and I have absolute value of f of x minus c, and absolute value is less than epsilon. So what does that mean? That means there are numbers f of x which are really, really close to f of c, which are also less than or equal to n. And like, that should mean that f of c is less than or equal to m, right? If a number is really, really close to stuff that's less than or equal to m, then that number itself should be less than or equal to m by taking the really, really close, really, really small. And let's go through those motions. Let's try to explain why that means that f of c is less than m plus epsilon. And let's start with this to do that. So let's see, since absolute value of f of x minus f of c is less than epsilon. We've done this in the past. But do you think you could take that inequality and solve that for what f of c is equal to? Sorry, I shouldn't have phrased that as a question. Do it. Solve that inequality for f of c. Get f of c is bigger than something. Something is less than f of c is less than something. You guys are just like really quiet. So what bounds do you get on f of c?
Lower bound would be f of x times by epsilon.
And the upper bound is?
Epsilon plus f of x.
Plus epsilon.
Or
Yeah, so maybe you took like the next step after that. So let's combine that with this. What's an upper bound I have on f of x? Have we just proven that f of c is less than or equal to m plus epsilon for absolutely every epsilon bigger than 0? Well, since f of x is less than m plus epsilon for absolutely every epsilon bigger than 0, we may conclude that f of c is less than or equal to m. How do you feel about that?
Does the strictness not matter?
I mean, it's strong law, right? If f of c is strictly less than m plus epsilon, then f of c is also less than or equal to m plus epsilon.
Mm-hmm.
So I mean, we actually get a stronger conclusion. So,
Mm-hmm.
I mean, the answer is no. Like, both of the theorems that you might write down are true.
Okay.
The proofs would be slightly different. One of them would require you to divide by 2 and the other one would not.
Okay.
People feel okay about this? And let's see if we can even convince ourselves that we should be able to do something similar on the other side. So this c is supposed to be the biggest value where f of x is bigger than m. C is supposed to be the biggest value where f of x is less than or equal to m. So if I look a little bit to the right, if I look at that x value, f of x has to be strictly bigger than m, because this x value couldn't possibly be in the set. But these f of x values should be really close to f of c. So f of c should also be really, really close to stuff that's bigger than m. So it must be that f of c is bigger than or equal to m, by the same sort of logic. That seem reasonable? I mean, now let's put words to that, those broad strokes ideas, and talk through it. So let's see, this picture, like, I wanted to take something a little bit to the right of C. But is there any law right now saying that C couldn't be equal to B? No. And if C were equal to B, I couldn't look to the right of B. I wouldn't even be in the domain of F anymore. Yeah. But wait, by assumption, what did I assume about f of b in the statement of the theorem?
It's bigger than or equal to.
Okay, cool. So I get my result regardless. Because all I'm trying to show right now is f of c is bigger than or equal to n. So it suffices to prove the result when c is strictly less than b. So we already know that we're going to play this game where we approximate. So I'm going to try to prove that f of c is bigger than m plus epsilon for every epsilon bigger than 0, because then I'll be able to conclude f of c is bigger than or equal to n. All right. Well, it'll be so we already know the logic's going to be similar. So step one is get the approximation down. That just means write down the definition of continuity. So there exists some delta, for any epsilon bigger than 0, there exists some delta bigger than 0, such that for all x in a comma b, if absolute value of x minus c is less than delta, then absolute value of f of x minus f of c is less than epsilon. So now, there are lots of x's in the interval between a and b. I need to pick an x value that's within a delta of c, but is also between a and b. That's the type of x value that I want to use. So here seems to be what it should walk. C plus a little bit so that it's a little bit bigger than c. C plus something that's less than or equal to delta over 2, so that it's within a delta of c. I guess here it'll be even within a delta over 2 of c. But also, I can't be any bigger than b, otherwise that x value isn't in the domain. So let's also add something that's a little bit less than b minus c over 2, so that x is still in the domain. It's still in between a and b. So there's the justification for the proof, but let's not just add these words. So just by looking at that, why should that value for x be bigger than c? Let's see, is delta over 2 bigger than 0? By assumption. Let's see, by assumption, delta is bigger than 0, so delta over 2 is bigger than 0. Why is b minus c bigger than 0?
Since b is greater than c, b minus c is greater than 0.
Yep. If I take the minimum between two positive numbers, is that still a positive number? Yeah, right. It's exactly equal to one of them. Thus, min of delta over 2 and b minus c over 2 is strictly bigger than 0, so x, which is equal to c plus min of delta over 2 and b minus c over 2 must be bigger than c. Everyone feel pretty good? All right, so that x is strictly bigger than c. Could that x value possibly be in the set big U? Why not? Because it's bigger than the supreme. The supreme is supposed to be an upper bound. No. C is an upper bound on U. Ah, but wait, remember, U is the set of all x values for which f of x is less than or equal to n. So if x is not in U, what can you tell me about f of x? So
It's greater than n.
yeah, so let's see, maybe you wouldn't want to write all of these. So x is not in the set of all x values for which f of x is less than or equal to m. So if this number x is not in that set, it better not, that means it does not satisfy this inequality. So f of x must be strictly bigger than m. Oh, well, this order is all along. This should probably come sooner. Because there's something wrong with that logic. What if x weren't even in the set a comma b? I couldn't evaluate f of x then. But happily, x is less than b. In fact, x is less than or equal to c plus b minus c over 2, which is the same as the average between b and c. That makes sense? Anyone want me to say more words justifying any of those steps? Okay. So let's see. That means x is less than b. Why should x be bigger than or equal to a? How does x compare with c?
It's bigger than C.
X is bigger than c. How does c compare with a?
Bigger than A.
Bigger than a. Well, or equal to. C might be equal to a. So, also, we've already seen x is bigger than c, which is bigger than or equal to a. So, x is bigger than a. Thus, x is in fact in the open interval from a to b, but all I care about is the closed interval. Why is the absolute value of x minus c less than delta? Well, I guess let's try to show it. Let's try to analyze absolute value of x minus c and see what we get. And let's start with this. Which is bigger, x or c?
X.
X by this step. So what can you tell me about the absolute value of x minus c? What is that equal to? Just x minus c. So let's see, maybe I'll even rewrite this. So that's the same thing as c plus the minimum of delta over 2, comma b minus c over 2 minus c. I think something cancels? The c's cancel? And let's keep our eye on the prize. I want that to be less than delta. Why is this less than delta?
Between delta over 2? Or the second one?
The whole thing.
Well, delta over 2 is less than delta, and then if the min of those two is b minus c over 2, then that's also less than delta over 2, which is less than delta.
Mm-hmm. The min of two things is always less than or equal to either of the two things? Cool. Ah, wait, but that means absolute value of x minus c is less than delta. So what can I conclude about absolute value of f of x minus f of c?
Less than epsilon.
Less than epsilon by that, I guess. And from here, maybe this seems like it'll be like almost the same as what we did previously. So since absolute value of f of x minus f of c is less than m, we get m minus f of x less than f of No, that's not an m. God damn it, that's an epsilon. Whew. We conclude f of x minus epsilon is less than f of c is less than f of x plus epsilon. And right now I want f of c to be bigger than something. So let's focus in on this lower bound. Do I know anything that is... Do I know that f of x is bigger than something right now? Because of this. So by 3.15, m is less than f of x. So I get m minus epsilon is less than f of c. So I've just shown that for every epsilon bigger than 0, m minus epsilon is less than f of c, from which we can conclude f of c is, well, no, let's write it this way. All right, just because of the way that's written. But wait, now I've shown that f of c is bigger than or equal to m, and f of c is less than or equal to m. What's the only number that's simultaneously bigger than or equal to m and less than or equal to m? M. So f of c is actually equal to m, which I claim completes the proof. Maybe let's actually check that this completes the proof. What was the goal? What's the conclusion of the intermediate value theorem? That f of c equals m, and I guess that c is in the closed interval from a to b, which it must be the case before you can even talk about f of c. So yeah, that's exactly what we, this does actually give us the desired result. How did that proof feel? So I think that this was probably, hopefully this was easier to follow than the proof of the extreme value theorem. Well, I mean, because of the pace at which I have to give it, right? There are always two levels of understanding you can have in a proof. Could you have come up with the proof yourself on the spot in the same amount of time? Maybe. I think that's a stretch of 50 minutes. On the other hand, did each step seem to follow reasonably well from the previous? Okay. So that's the level of understanding that I think I'm going for this one. So we've got 5 minutes. I think that's not enough time to start it on another note packet, regardless of what I did last time. So instead, I suggest the following. Here's a result. Suppose you have a continuous function, f from R to R, a continuous function, and the image of f has no upper bound and has no lower bound. Then I claim that f is a surjection. Alternately speaking, is onto. Let's try to come up with an idea for a proof of that. Let's start with this. Who remembers what onto means?
There exists an x in the codomain such that, oh no, for every x in the codomain. Never mind.
Yeah, that's good. For every x in the codomain, which is, I guess, this copy of R,
There exists a y in the other R.
there exists a y in the domain, this kind of R, such that
F of y is equal to x.
and that's a perfectly correct way to write it, but
Yeah.
f of x should be y, not f of y should be x. So I guess
Switch those.
So for every possible y value, there exists an x value with f of x equal to y. And now you even like get the definition that like a pre-calc student would want, like something about for every horizontal line, there exists at least one x value which has f of x sitting in that line. Okay, cool. So that's what we want to show. So how should a proof of this go? I want to prove something is true for every y value.
Consider any y values.
Nice. So that looks an awful lot like the conclusion of the intermediate value theorem, doesn't it? Like the intermediate value theorem produces an input which gets sent to an output, provided that output satisfies some assumptions. Like the output needs to be between f of a and f of b for some choice of a and b. So in order to do this, because right, if you could do that, then you could say, aha, by the IVT, there exists some x in the interval from a to b with f of x equal to y. I don't care that it's in the interval from a to b. It's nice that you get that, but you don't really care. The interval from a to b is contained in R. And right, my goal today is like to give this proof. I want you to think it through, but let's see how we can come up with ideas. What's the thing we got to assume about this function?
It's continuous and unbounded.
It's continuous and unbounded. Let's think about that unboundedness. Could this y that you chose possibly be an upper bound for the image of the function? No, it's got no upper bound. So that, I don't think I'm going to write anything more. That y value isn't an upper bound. So there must be something in the image of the function which is bigger than f of y? Nope. There must be something in the image of the function that's bigger than y. Do you think that gives you either that or that? I think so. Could this y possibly be a lower bound on the image of the function? Also no, for the same reason. Well, basically the same reason. So do you get an f of a that's less than y? That's less than f of b? If a and b happen to be in the correct order so that a comma b is an interval, there you go. What do people think? Is that enough information to come up with a proof? And a lot of the proofs for the other ones will be similar in spirit. So if you want to come up with an application of the IVT, even if you don't know what the function is, try to use the assumptions about the function to come up with these a's and b's. Nice. So, and I guess my other ostensible goal was to start talking about uniform continuity, but I'm going to leave that. Remember to bring that note packet. Maybe even look at that note packet over the weekend. Anyone have things they want to give me right now? Cool. Let me stop recording.